If you're a student at my course, you have hopefully seen that in my compendium there is towards the end an ultra short summary of my parts of this course. And what we will do now is a quick summary of what comes at the written exam in my part. So, disclaimer first, this is a summary about central topics and does not cover everything. At the written exam, you're expected to be able to prove that you understand underlying theories and principles as well. And you might also need to show that you understand concepts from previous courses, just as you do in some of the exercises you hopefully have done by now. So we started out my part with the air-water system, so moist air. We learned how to use the psychrometric chart, also called the Mollier diagram, with heating, cooling, cooling below dew point, mixing. And to do this, we needed to make mass balances and for some also energy balances. And the crucial thing was then the units. We will come back to that. We also looked at the wet bulb temperature and realized that that is an energy balance between evaporation from a water surface and heating by the surrounding air. So when you do mass balance, it's an energy balance, a really critical thing, and this you definitely need to understand. And many people have failed my exam by not understanding this properly. You have to understand what unit you can use for mass balances and energy balances. So for mass balances, it's kilograms or kilograms per second. If you're clever, you might be able to use mole or mole per second. For the moist air, likely not. It will become messy because the Mollier diagram is given in kilograms. So better stick with kilograms and kilograms per second. What you should never do is to use mass balances in cubic meters or something like that. So cubic meter per second. That doesn't make sense. Especially not if you deal with gases. PV equals nRT, ideal gas law. If you change the temperature, you change the volume, right? So never use cubic meters. For energy balances, you need to make sure that the unit you use is an energy unit, right? So you need to have joules or joules per second. You can't have Celsius or Celsius per second, Kelvin or Kelvin per second, or some strange kind of thing like kilojoule per kilogram and cubic meter and something strange. So when you make a mass balance and an energy balance, be sure to check what unit you use and check that is that a good unit. You can save a lot of points at my exam by doing that carefully. Then we turned into mass transfer, and the first we did was to learn how to estimate transport parameters. So diffusivity in gases we use this equation for, and the order of magnitude should be 10 to the power minus 5 square meter per second. For liquids, we learned how to use two different equations, the Stoke-Einstein equation for large molecules and the Wilke-Chang equation for small molecules. And the order of magnitude there should be typically less than 10 to the power minus 5 all the way down to 10 to the power minus 12 square meter per second. The large range because different liquids are really different. Some are almost like gases and some are almost like solids. Then we turn into transport in one dimension. And we use this equation here with the diffusive part and the convective part. And we derived two special cases. Equimolar counter diffusion, where you get a linear change in concentration, and diffusion through stagnant component, where you get a non-linear change in concentration. We introduced several dimensionless groups. You already know Reynolds number before, and we introduced these three very important dimensionless groups: Prandtl number, Schmidt number, and Lewis number. which relate different diffusivities to each other. So mass diffusivity, heat diffusivity, and diffusivity of momentum. Then we turned our attention to different mass transfer theories and analogies, and we introduced 3 different theories. The two-film theory for situations with more or less undisturbed and well-defined films. The penetration theory, when you have a film that only survives a short time, like when a gas bubble rises through a liquid. And we introduced the boundary layer theory, which you can use when you have a flow that meets a surface, and then you describe what happens at a certain distance from the edge. And then we introduced analogies as well, Reynolds analogy and Chilton-Colburn's analogy, that doesn't involve diffusivity. It instead relates different transfer coefficients. So the mass transfer coefficient to the heat transfer coefficient and to the transport coefficient for momentum. So when we looked at that, we looked at the convective flux in one direction and related that to the diffusive flux in the direction orthogonal to the direction of the flow. And to be precise, it's not necessarily only the diffusive flux orthogonal. It can be a mixture there. If it's not laminar flow, if it's turbulent flow, then what happens in the direction diagonal to the direction of the flow is both actually convection and diffusion. So the 3 theories, they relate the mass transfer coefficient to the diffusivity in some way. So in the two-film theory, the mass transfer coefficient is proportional to the diffusivity. For the penetration theory, it's proportional to the square root of the diffusivity. And for the boundary layer theory, we said that it's proportional to diffusivity to the power of 2/3, but it actually changes if you have turbulent flow. So it's actually not the same for laminar and turbulent. But the important thing to realize there that it's the relation between mass transfer coefficient and diffusivity is dependent on the situation, what kind of theory that is applicable. So an important lesson there is to realize that if I know how the diffusivity changes, if I change the temperature and the pressure, I can actually tell something, make a prediction of how the mass transfer coefficient will change in that situation. In the Reynolds and Chilton-Colburn analogy, as I said, they don't include diffusivity at all. They only relate transfer coefficients to each other. So the mass transfer coefficient to the heat transfer coefficient and to the transfer coefficient for momentum. Next, we looked into distillation, and we learned how to use McCabe-Thiele's graphical method for solving distillation problems involving binary systems. And there were a number of assumptions behind that, and those assumptions you should know at the exam. In McCabe-Thiele's graphical method, we find first a system diagram that someone has drawn for us. Then we draw the diagonal through that. So the system curve is the relation between the composition of a boiling liquid and the composition of a condensing gas, if these two, the liquid and the gas, is in equilibrium with each other. So once we have the system curve and the diagonal, we draw the upper operating line, which is a mass balance. We draw the Q line, which is a combined mass and energy balance for the feed location. And then we draw the lower operating line, which is a mass balance of the lower part, the part below the feed. And then we draw steps. And each such step, each such triangle is an equilibrium stage where the outflows are in equilibrium with each other. The Q line, as I said, is a combination of a mass balance and an energy balance. And we have this equation. You don't need to be able to derive this equation, but you need to understand how to use it, to understand what Q is. And in our course, we limit ourselves to situations where you have saturated liquid or saturated saturated gas or something in between. And the rule of thumb to remember which is if you have a vertical line, that line has the same composition in the liquid phase, right? The x-axis in all points of the line. So that line has something to do with liquids. So hence saturated liquid has a vertical Q line if the feed is saturated liquid, and if the feed is saturated gas, so gas at its condensing point, then the Q line is horizontal. Then we also talked about physical trays and tray efficiency. You always have more physical trays than you have equilibrium stages. And on an exam, if I ask for equilibrium stages, you should answer with 1 decimal. So I understand that you understand that equilibrium stages you can have 0.2, for example. With physical trays, you need to round up to the nearest integer, so 13.2, round that up to 14, because you can't have 13.2 physical trays, just the same as you can't have 0.2 shirts. Doesn't work. When you calculate tray efficiency, make sure that you deal only with the column, what happens inside the column, because you also have things outside, typically, condenser and reboiler. A total condenser does not add anything to the separation. It's not an equilibrium stage. There's no separation there, but it's needed still. The reboiler though, we say in this course, for simplicity, that that's exactly 1 equilibrium stage. And the same with the partial condenser. We say that that's exactly 1 equilibrium stage. And to calculate or to use the tray efficiency, you need to make sure that you're dealing with what happens inside the column. Finally, the feed location. That is the triangle in the diagram when you start at the upper operating line and you end up on the lower operating line. And if you want to place this optimally, so to get as few triangles, as few equilibrium stages as possible, you should shift between the upper operating line and the lower operating line as soon as you have passed the intersection between the 2 operating lines. And you can figure that out just by thinking of it geometrically. So that was a quick summary of my part of the written exam. And when I correct the exam, I will deduct points for, of course, errors. When you don't show that you understand the problem, when I can't follow your solution, and also for careless mistakes. And an extreme example of careless mistakes is that I once had an exam with 100 students, and 9 students, when they tried to translate 10 minutes to seconds, they translated it to 1/6 of a second. So dividing with 60 instead of multiplying by 60. And I understood that, yeah, that's a careless mistake. They actually understand. But it's important that you understand your weaknesses. And if you're like me, prone to make careless mistakes, you need to be aware of that. And that's a weakness, just as not understanding theory is a weakness. So if you don't understand theory, or if you make careless mistakes, those are both examples of things that can result in accidents and other tragic stuff. So I deduct points for both of those things.